Welcome to today's edition of ROHDE SCHWARZ 35. The presentation of today will be on measurement topics and hints for power electronics. In power electronics, there are some typical steps converter or inverter designs are happening. First, the actual switching devices have to be checked. So it's important to understand sub-circuits, to understand timing, gate timing, and usually this is done in the first place without DC link voltage applied. Because only if it's sure that the basic switches are working correct and there's no shut through or anything else like that happening, then it's possible to move to the next step and applying DC link voltage and then checking for the actual voltages on the switches, like if FET ratings and so on are exceeded or not. After that, after it is ensured that the basic converter can work and is set up in the right way, usually the next thing to consider is passive components. Are they working in the way as one expects? Or are there any kind of saturation effects? Or is the capacitor behaving as it was expected when designing the circuit? If that one works as well, then usually the view is more on the system level, so analyzing, okay, what about startup, what about load variation, efficiency, stability, and so on. And if that one is done, then usually one of the next things happening is taking care about environmental checks. So what about thermal things? What about DC link variations? Does the circuit really work, or the converter inverter really work in all the different kind of temperature settings that it is specified for? And last but not least, EMI analysis has to be done, conducted and both radiated. For all those topics, there are some basic considerations that are important. First of all, probing is one of the key topics, because the probe is the element which basically takes the signal and conditions the signal in the right way that an oscilloscope can measure it. Yeah? The probe will determine how accurate measurements are, what kind of ringing or extra ringing is there, so to what extent the measurement really reflects the truth. Yeah? So that's topic number one that is really important. Moving forward, for example, looking at analyzing passive components or doing some advanced analysis, understanding how the circuits work, the MAF functionality of the oscilloscope becomes important. Next step, often when you look at system level behavior, there are some dedicated analysis functions that are very handy, like body plots or PWM analysis or similar things that make life easier. And if this kind of analysis capabilities are there, then then basically things can be done in an easier way. Last but not least, going to EMI analysis. It's important that the oscilloscopes one is using is also capable regarding FFT performance, because if this is the case, then you can already analyze EMI topics on the R&D designer's desk without the need to move to some dedicated pre-compliant setup and do optimization work or design work already there. Now looking at probing. Well, I would like to touch a few topics here. Number one, floating measurements, how to perform floating measurements, some basics on common mode rejection ratio, and also discuss which probe is the right one for what measurement. If you look at floating measurement techniques, well, the most basic one, which actually cannot be recommended, but still is sometimes seen, and in rare occasions might be the right thing to do, is floating the scope. Floating the scope means that somebody is using an isolation transformer, for example, so to cut the ground connection of the scope to the actual ground connection, which basically makes it possible to, for example, measure with a passive probe in a floating manner. However, the difficulty here is that if you connect the passive probe in the wrong way, the whole oscilloscope can have dangerous voltages, hundreds of volts on its chassis, which can be a serious danger to the people working with it. That's one thing. But the other thing is that actually the signal quality is not good, because isolation transformers do not provide a good isolation also for high frequencies, and this leads to some coupling effects which are kind of unexpected. But I will touch this topic a little bit later in more depth to understand what are the difficulties, and also where does it still make sense. But at this point in time, basically the answer is floating the scope is not recommended, and the most important reason for safety reasons. Well, then there is the method called A-B, which means you use two passive probes and you just use the capability of every scope at the end there, who can to subtract channel 1 minus channel 2 and make a differential measurement with that. Well, the difficulty here is that this might work for low frequency measurements with low common mode signals, but as soon as the frequencies are higher, or the switching speeds are higher, or the common mode signals are higher, it doesn't work anymore. So for high common mode signals, you will likely overdrive the input amplifiers, so you won't see the actual differential signal anymore. And if the switching frequencies are high, you have the problem that any kind of non-symmetry between the probes will directly go into a reduced common mode rejection ratio. So this method, although it sounds easy and can be done with simple probes, is definitely not recommended because of performance reasons. The standard way and the recommended way how to do these measurements is to use high voltage differential probes. They are designed to measure small differential voltages in a safe way, and also in the presence of large common mode voltages, so that you can reliably measure. You have a small input capacity, you have a big input impedance, and as mentioned before, it's a safe way of measuring. So that's definitely the number one way of how to measure differential signals, of how to perform floating measurements in power electronics. The other option is to use an isolated channel oscilloscope. Isolated channel oscilloscopes, these are usually handhelds. They have input channels which are galvanically isolated between each other and between the rest of the instrument. And this galvanic isolation is usually done in a way that there is only a small coupling capacity between the channels, or between the channels and the main instrument. So the one thing that is achieved here is that it is a safe measurement, because the channels are isolated and also kind of proven to be safe up to 1000 volts or more, and you also get a good common mode rejection ratio, so a good suppression of common mode signals, and you don't have a small influence because of other coupling effects. So this is definitely another method for making floating measurements. Well, you don't achieve the same common mode rejection ratio as with high voltage differential probes, but you can also get very good results, and for a lot of devices where switching speeds are not extraordinarily fast, you can get very good measurements. And of course, the other aspect here is that for handheld instruments, they are particularly valuable if you go to like field measurements. For example, if you have to debug problems on an inverter that is sitting at a solar station, or you have to debug something on a big electric drive at a customer site, that's definitely the sweet spot for such an instrument, but also used sometimes in R&D. Well, coming back to floating the scope, apart from the safety topic, there are other things to consider why this is really you have to be careful with such a measurement. One thing is that not only can the scope carry high voltages on its chassis, it's also simple or that you break the isolation. For example, if you hook up a communication cable, so a USB cable, LAN cable, RS-232 cable or whatever, from the scope to your notebook, then you have no isolation anymore, because your notebook might be grounded, or if your notebook is not grounded, then also your notebook might float up to voltages of a few hundred volts, which is really dangerous. And often in such settings, oscilloscopes are controlled via remote interface, because operation of the scope might not always be something that you want to directly in front of it because of the safety topic. Well, but apart from that, it's also performance-wise there are difficulties, and the reason is that the isolation that a typical isolation transformer provides does only work for DC and maybe for low frequency AC. As soon as the frequency, the switching frequency, the frequency components that you want to measure are significantly higher, such an isolation transformer is actually much more like a direct connection than like isolation. And this means you have the oscilloscope still grounded, and you generate some kind of ground loops or other couplings that you didn't want to have, and that severely influences your measurement. So measurements results will not be good. Well, comparing all the methods. So as mentioned before, floating the scope is first of all dangerous, even though that sensitivity, accuracy, bandwidth, all those things can be achieved in a very good way. But common mode rejection ratio is usually also not great. Yeah? Where can you still do it? Well, number one, this should only be done if it's behind a safety screen, and if you really make sure that that the remote control that you do is done with some kind of isolation transformer for LAN interfaces, which are also available. And you should really consider what is the coupling that the isolation transformer for the main supply of the scope introduces. So those are things to consider. But if you considered that, and if in your particular application this is possible, and you considered all the different safety aspects, it might still be a viable measurement. Well, A minus B. For A minus B, you don't have safety issues, or at least it's not inherent unsafe. Sensitivity is good, but everything else performance-wise is not great in such a setup. So therefore such a measurement doesn't really make sense, because you don't get good measurement results. As I mentioned before, high voltage differential probe is the way to go for floating measurements. You achieve bandwidths of typically 200 megahertz. The limit here is not only the probe, so typically high voltage differential probes are only available for 200 megahertz, but even if you push the bandwidth of such a probe to higher bandwidths, to 300, 400 megahertz, usually you will get severe limitations because of the connection. So if you have, usually you have on such probes 4 millimeter connections and cables and maybe some kind of alligator clips or something, this kind of connectivity will not allow for good measurements above from 200 megahertz. Yeah. Well, accuracy is very good, safety is very good, and the common mode rejection ratio you achieve with high voltage differential probes, if you choose the right models, is also very good. So it's generally recommended to make measurements, floating measurements in that way. And the isolated channel scope, as I mentioned before, is also an excellent solution. Typically, the sensitivity is even better for high voltage differential probes, because you can use the supplied 10-to-1 passive probes for such measurements, whereas high voltage differential probes are usually only available with 50-to-1 or 100-to-1 attenuation. And the other aspect is that isolated channel scopes have a very high bandwidth compared to high voltage differential probes. They often go to, so the latter one the isolated channel scopes often go up to 500 megahertz. But if you look at common mode rejection ratio, this is not as great as for high voltage differential probes. So there are some limitations. Okay, let me dive a little bit into the topic of common mode rejection ratio, some basics. Yeah. So, well, the main reason why common mode rejection ratio is important is, of course, that one of the typical measurements people have to do in power electronics is measuring the gate source voltage on a high side switch. And the problem there obviously is that the source pin of the MOSFET is often switching with high voltages that can be up to 1000 volt, and on top of this voltage you have to measure the gate source voltage. This means you have to suppress the 1000 volt switching common mode voltage in order to measure maybe the 5 volt signal that is differential. This means you have a high common mode rejection ratio that is required. Well, now what is important to consider here? Number one, the first thing that is important here is to understand what is the bandwidth of your signal. And the bandwidth of your signal depends only on the rise time. So you can approximately say that 0.4 over the bandwidth is the rise time, or vice versa, 0.4 over the rise time is the bandwidth. So if you have 400 nanosecond rise time, the bandwidth of the signal is more or less in the order of 1 megahertz. If you have 40 nanoseconds, the bandwidth that you have to measure is 10 megahertz. And if you have 4 nanoseconds, so a really fast switch, then the bandwidth you consider is 100 megahertz. So this is one thing that we need now in the next slide then. Then the second topic you have to consider is what is actually the common mode rejection ratio that I need. And this of course depends on the switch node voltage swing. So if the switch node voltage swing is only 10 volts, and I assume now that 1 volt of remaining common mode signal is still acceptable for the measurement, then 20 dB suppression would be fine. 100 volt would mean 40 dB suppression is necessary. 1000 volt would mean 60 dB suppression is necessary. Okay, now we can take those two informations and look into the data sheet. When you look at typically high voltage differential probes, you find out that common mode rejection ratio of course depends on bandwidth. So typically you see that up to a bandwidth of 1 megahertz, a common mode rejection ratio in the order of 60 dB is achieved for quality high voltage differential probes. If you go up to frequencies of maybe 200 megahertz, then you see that common mode rejection ratio of 40 dB, so it drops down to 40 dB. Now looking at the voltage swing discussion that we had on the previous slide, you can see that, well, 40 dB is sufficient if you have a switch node voltage of 100 volts. 60 dB is required if you have to go to 1000 volt. So, and this gives you now a hint to understand, okay, what can I actually get with my probe, or what do I need, or what kind of result can I expect? Now, looking on the other side, on isolated channel scopes or on broadband differential probes, there are some other interesting things you can see. Isolated channel scopes usually have a very good common mode rejection ratio if you go to very small frequencies, because since they're isolated at DC, the common mode rejection ratio is more or less perfect. Then when you go up in frequency, one can say that up to a measurement frequency or signal frequency of 10 megahertz, you can see that, well, common mode rejection ratio is still pretty good, and then it gets a little bit erratic and depends on a lot on the exact setup. Yeah. One of the reasons for that is isolated channel scopes are not symmetric, and when you use passive probes, which are also not symmetric, at some point in time regarding frequency, common mode rejection ratio cannot be great anymore. The other thing is, when you look at broadband probes, you find out that sometimes they might be also very interested for power electronics applications, in particular if the voltage swing is not so high. So broadband probes are usually available only for ±5 volts, but there are models that accept an additional external attenuator, which makes it usable for a voltage swing of up to ±50 volts. And then if you consider the additional offset, you can theoretically measure from 0 to 100 volts with a broadband differential probe. Now, the other advantage of a broadband differential probe is that, well, since it is actually designed for high-speed signals, those probes have bandwidths of 1 gigahertz, 2 gigahertz, so really wide bandwidth when you consider power electronics. The common mode rejection ratio of such a probe is not as great, but you can see that it is in the range of, and this is now a measurement that was done with one individual probe, that it is in the order of 60 to 50 and maybe at the end 40 dB. Looking again at the switched mode voltage, you can see that, well, that makes sense for voltages up to 100 volt, which exactly tells you that this is the application where such products might make very much sense. So considering like converters or inverters working maybe at 48 volt maximum, broadband differential probes might be a very interesting choice for floating measurements. Well, let me briefly touch an overview about probing solutions. So which probes to use in what situation? Well, I touched the broadband differential probes already, so bandwidth is usually very good. One big advantage is that since they are designed for broadband designs and not for high voltage natively, the connections that you can make with such a probe are usually very short. Yeah? And this is always one critical point in probing for power electronics, so that's an interesting advantage. And common mode rejection ratio for the voltages such a probe can measure is still pretty good. But you have to, the con of course is that it only works for lower voltage design. So might be interesting for gate driver measurements and fast lower voltage designs. Then there is a category which I would give the name of standard high voltage differential probes. They are also available from us, but this is a basic product, so relatively inexpensive with BNC interface. They have bandwidths in the range of 25 to 100 megahertz, and common mode rejection ratio is not really great. But if you have not really high demand, such a probe might be still sufficient. Yeah? But if you care about common mode rejection ratio, then there is the category which I would name as high common mode rejection ratio, high voltage differential probes. They are particularly designed for that. In our case, this is the probe family RT-ZHD. And as I mentioned before, this is the #1 choice for floating power electronics measurements. Important parameters is bandwidth, common mode rejection ratio, low input capacity, of course. Yeah. Passive probes, you should also consider passive probes. I mean, they cannot measure floating, at least not in a safe manner, but sometimes floating measurements are not required. And in that case, passive probes are really an interesting choice because they are relatively inexpensive and they have a high bandwidth available. Well, and then the isolated channel scope, which is also used in combination with passive probes, is a kind of a category for its own because it is a relatively inexpensive solution with a medium to high common mode rejection ratio on the pro side, also independent from main supply. What is important to consider here is that you usually need some manual work to make a good connection. But if you do that, then you can achieve pretty good results with such a solution. Typical applications, for example, where mobility is needed, budget is limited, or you still need quite good measurement results, that might be a perfect solution. Well, what else is important? I briefly touched that one before. So keep connections short always. The problem is that the connection of a probe, so if you would imagine such a connection of a high-speed probe, for example, to a device under test, this connection, this kind of loop the connection forms, creates an inductance. And this inductance forms a resonancy together with the capacities involved, and this leads to ringing. And ringing is exactly the one thing that, of course, you want to avoid, because it will distort your measurement. And if you have extra ringing because of the probing, you do not know anymore if the ringing is because of the design, of the layout, and there is some, maybe you are touching already the maximum voltages that the MOSFET can withstand, or if this is just fake because it's only because of the probing. So connections always have to be short. On the left side, you see a measurement setup with a passive probe with long connections. That's definitely something you should not do. On the right side, two examples. That would be a spring tip measurement. That's not always possible. Sometimes, in particular for higher voltage applications, there you should go for something that you can solder in order to be safe. Or if you use the passive probes of an isolated channel scope, this is a way how to connect those probes in order to get good quality measurements. Also on regarding common mode rejection ratio. Okay, topic number 2, I briefly want to touch mathematics functionality on oscilloscopes with 2 use cases, because this is important and very, very valuable sometimes. And I want to show you 2 things that you can do, and there is much more that you can imagine that you could do with an mathematics function of oscilloscope of an oscilloscope that is powerful enough. And such kind of functions you usually find in lab class oscilloscopes. So number 1 topic is in-circuit characterization of passives. This is something that I think is always interesting to power electronics engineers, because you want to understand how does the passive behave in the circuit in real life. And I mean, for inductors, one of the topic here is, for example, saturation. So if the inductor gets saturated because of the DC current flowing through it, the differential inductance which you need in order to store the energy is reduced, and therefore the inductor does not provide the inductance anymore that you would expect. Now on the right side you can see a simple example where we used math functions in order to make some kind of comparison. We looked at the measured current through an inductor, and we created a computed current, what we would expect, and compared that one. So that is one thing, but you can go further. You can also say, well, let's calculate the inductor out of the measurement, because you can make a differential, so measure or calculate di over dt, and then estimate the inductance out of the current measurement. And those kind of things give you a way of understanding what is actually the true behavior of the passive in the corresponding measurement or setup design. Another example is, for example, looking at currents in parallel to MOSFETs. One of the difficulties you often have is that you cannot really access the current with a standard current probe. So you have to go to like Rogowski probes, what you can see on the right side. In that case, a probe from PM UK. Those probes have the advantage that you can feed them sometimes between the pins of a MOSFET in order to measure the current through the MOSFET. However, the difficulty is that such probes can only do AC measurements. So you have the uncertainty about the DC value, and the other difficulty you sometimes have, you cannot access everything. Yeah? So in the example that I have on the screen, there is on the one side I was only able to access the sum current and one individual current. So I had to do, this is still simple math, to subtract the one of the other in order to compare the two currents. But there's some other trick I used to make the measurement easier, because in this experiment, which is a double pulse test, as you can see, I was using a gated measurement in just before the actual double pulse test happens. What I know here is that in this part of the signal trace, I know that the current is 0. And even though the measurement signal that the Rogowski probe provides me does not show 0 current, because a Rogowski probe cannot show the true DC current, I know that it is 0, and I can use this measurement in order to calibrate my trace. And this allows me to kind of stabilize the trace and then make measurements always reference to kind of some virtual DC value, just because I know what the DC current in the beginning of the measurement is. And for those kind of things, a powerful math function is important. What about other capabilities? Well, if you look more on the system level, then you typically need more advanced and kind of specialized measurement capabilities. One of them is stability analysis, another topic is PWM analysis or harmonics, yeah? And I will briefly touch this. So stability analysis, so doing body plots with oscilloscopes, can be done, well, first of all, you need the corresponding analysis software, which some oscilloscopes provide. And then this kind of software is using the generator output in order to generate a stimulus signal to the device under test, which is basically the control loop of your switch mode power supply. And then you measure channel 1, this disturbance signal, and channel 2, you measure the output signal of the DC power supply, and the scope uses that in order to calculate the body plot. Now looking into a result, so what the scope is of course doing, it changes the frequency of the steering signal and then performs the measurement, and out of the measurement it calculates on the one side the gain curve of the control loop and on the other side the phase margin, and based on that you can then derive, okay, number one, what is the phase margin, so the actual phase margin at the point 0 dB, and on the other side, what is the gain margin at the point where the phase is 0 degrees, so the remaining phase to like positive feedback is 0 degree, and those are the two important points, of course, for control loop stability. What is also important for this kind of application, that you can use amplitude profiles for the steering signal. This means you can change the value of the steering signal depending on the steering frequency, and this is necessary in order to get a good measurement result. What else? Another example, looking at a resonant converter in this example, is to consider the control loop itself, what happens in case of step responses, what happens, for example, in a startup phase. And for that kind of analysis, it's valuable to look at the modulation of the control loop. So for a resonant converter, the way how the converter is controlled, of course, is by frequency. So by changing the frequency, you change the energy transfer from the one side to the other. Yeah. So what I have here is I was looking at startup, so you can see output voltage and output current in the startup phase. You can see the switch node output, so that's the half bridge output. Below you see a zoom it's a zoom into this small zoom window, just that you see what is happening here in the beginning. And the middle part is really the interesting part here, because it shows the frequency of the converter over time. And as you can see in the beginning, the frequency is not stable in the startup phase. And the reason for that is that it is always switching on and off. And you can also see this down there in this zoom window. After some time, you see that the converter has stabilized, but still does not have reached the point of kind of where the end of the startup has happened. So the end of the startup phase basically starts here. This is where the converter is in kind of a steady state, and the remaining thing happening in the steady state, in that case, is only the remaining ripple of the DC link, which has to be compensated by the converter, because if the DC link voltage gets lower, then the converter has to transfer more energy, or actually has the same energy, but the transfer of power has to be higher in order to compensate for the lower voltage. That's basically the thing. And this kind of analysis allows you to look into those details and to understand what is happening. Yeah. Now, what is important here, you need deep memory. Number one, the startup phase here is 160 milliseconds, and but still at the same time you want to look into the details. So we have a rise time of 100 nanoseconds that we might still want to see sufficiently resolved in time. This means there has to be the memory in order to capture all that. And then, of course, there has to be the capability to analyze this frequency track. Yeah? That's the other thing. Another use case I will quickly touch, and as example I have chosen here the handheld, is that harmonic analysis is often important. What you want to consider is, or want to look at, is what are current harmonics, because there are some limits that you have to observe. And you can do this also with some kind of FFT analysis, but it's actually very convenient if you have an harmonic analysis functionality that provides you directly the magnitude, phases, frequencies of the different harmonics, and maybe also THD measurements. This makes life a little easier. Last but not least, FFT performance is important, and what I would like to touch here is that why is that important for scopes, and why is it important to consider scopes for early EMI debugging, and then I would also touch a brief case study on that one. Well, if you look at EMI debugging, or in the general development process of a product, well, of course, you started in R&D, then there's a prototype phase, pre-production and manufacturing. And for the EMI topic, you might start with simulation sometimes. Definitely you have to go into pre-compliance and debugging, at the end into compliance just before you start mass production. Now, when you look at the instruments that are involved, that you have on your table in the different design phases, you find out that you might have simulation tools. So you might already consider EMI also from a simulation point of view. Then in the actual R&D phase, the number one instrument for power electronics is the scope. So you will have a scope on your place. You might have a spectrum analyzer in a pre-compliance setup that you always use to make pre-compliance measurements. And of course, there has to be an EMI receiver, maybe in your own EMI chamber, maybe at a test house that you use at the end to make sure that your product is really compliant. But looking at the instruments, it makes very much sense to use the instrument that you have available in the particular phase. And if you are in R&D, it makes sense to use the scope for EMI debugging and troubleshooting if the capabilities are there. Now, what are capabilities? I will touch a few things. Well, one of the important advantages of scopes is that you can look at time domain and frequency domain at the same time. This means you can make correlations. You can see if something happens on the in the time domain, what is the effect on the frequency domain? What is the effect on some kind of emissions? Yeah. What if I change my slew rate? What if I change my filter? How does this affect EMI? Yeah. And it's also something which you can use for debugging if you see that in a pre-compliance measurement you have seen some difficulties. Okay. One example that I want to share here is a very important EMI for wide bandgap switching, because signals get very fast, and then there has to be some kind of trade-off of, okay, how fast do I make the switching, and what is the benefit I get in EMI, and what is the right trade-off. This is something you can do nicely in a scope. On the left side, you can see an example where we had extremely fast gate signal. Of course, this is not a thing that you would use, but so there's a lot of overshoots there. And you can see a lot of high frequency EMI. On the right side, just for purpose of demonstration, we used kind of a shaped gate driver signal. And you can see that, okay, the high frequency EMI was significantly reduced. Yeah. So playing around with that is something that you can do in an excellent way on your R&D desk. Yeah. Now, looking at EMI filters, this is another aspect that you can consider with a scope. Usually you would use some kind of listen because you need to measure conducted emissions. In this example on the left side, you can see, okay, there I did a measurement with a power supply just for purpose of demonstration without the EMI filter. On the right side, you can see that the measurement with input filter, so EMI filter. So you can see that, okay, obviously there is an effect that of course has to be there because of the EMI filter. But now the thing that you can do is, okay, let's look at the details, let's change something of the filter and understand what is my effect on the conducted emissions. Yeah? And you don't need a perfect setup here. There are a few rules that you have to consider. So you should place your setup, in particular the listen, on a metal plate in order to make sure that it has to do something with typically pre-compliant setups. But if you have a somehow sensible setup, then you can make pretty good measurements that let you judge, okay, what do I have to do with EMI input filters, what do I have to change, what is the effect if I do this and that. Yeah? And this is exactly the work that you can do in a good way in R&D with an oscilloscope. Yes, this brings me already to the end. Thank you very much for listening to my presentation. If you're interested in further information, please follow the link below, and you will find this is the solution page that we provide for power electronics testing. There is a lot more information on control loop stability, general stuff on verification and debug, EMI debugging, and also something on efficiency testing and switching analysis. Thank you very much.